All right, so continuing on. Welcome back. Second half of this video for limits involving infinity. So for this one, I want to look at this example. We have the limit as x goes to infinity. This time I have 3x to the fifth minus 2x plus 1 over 4x squared minus 2x plus 6. All right, so this is where it's going to start to get just a little bit interesting. We now have a higher power on the top than we do on the bottom. And so if we divide everything, we could do that. But it turns out if the power on the top is bigger, we need to treat it just a little bit differently. And I probably should have just said this earlier. Always divide by the highest power in the denominator. Don't worry about the numerator. Divide by the highest power in the denominator. If we do that, we divide everything by x squared. I get 3x cubed minus 2 over x plus 1 over x squared, all over 4 minus 2 over x plus 6 over x squared. Again, I'm dividing each of those pieces by that x squared because that's my highest power in the denominator. Which is great because now if we start thinking about this limit as x goes out to infinity, these four fractions are all going to drop out because they all go to 0. And we're left with the limit as x goes to infinity of 3x cubed over 4. And guess what? That is infinite. So if the power on top is bigger, it turns out you get what's called a slant. Well, you could have a slant asymptote. This is definitely not going to be a line that it approaches. But it will go to infinity for basically forever. So yeah, that's pretty, it is what it is. It's fun. All right, let's look at this one. Now we have a definition. The definition, we say that f of x goes to infinity as x approaches c, and it's written as the limit as x approaches c of f of x is equal to infinity if for every positive number b there exists a delta greater than 0 such that 0 less than the absolute value of x minus c less than delta implies that f of x is greater than b. Whew, that's a lot of stuff. All right, so basically we're squeezing these functions again. So with our normal limit, we say if you can get as close as you want to that limit if you squeeze in close enough on the x value. So in this case, since we want to show that this limit is infinite, we can't very well squeeze in on as close as we want to infinity. That doesn't really even make sense. So instead, what we do is we start by saying, hey, we just needed to get as big as we could possibly want. So b is just a number. We can get past that if we squeeze in close enough to c. So here's that delta again that we've seen before that's establishing this little tiny space around where we're taking our limit at for c. And what we're saying is if you squeeze that close, you get up past b. Now, again, since b can be anything we want, that means that this function has got to keep going up forever right there. It's got to be going up towards infinity because you can make that function be as big as you could possibly want it to be as long as you squeeze in close enough on c. So I'm going to do an example where we prove a limit, and then we're actually going to be pretty close to being done. It also turns out that if you have this limit that is at a number that is infinite, you get a vertical asymptote. The actual definition says for a vertical asymptote says it just has to be either from the right or from the left. You've probably done some rational functions and their graphs. Sometimes they go in the same direction, but sometimes they flip and go different directions, and that's okay. As long as the one side of the limit is going up to infinity or down to negative infinity, we're going to have a vertical asymptote. All right, so let's look at my example next. All right, so here's my proof of a limit that goes to infinity. That should not be 0. I wrote that wrong. Let's make that an infinity sign. There we go. That's better. Prove that the limit as x goes to 0 of 1 over x to the fourth is equal to infinity. So let's start by picking some random b that is positive, right? Remember, the idea is we're going to find a delta that squishes us in close enough so that we get past any number we want. In this case, we call it b. So we're going to find delta st by such that 0 less than the absolute value of x minus 0 less than delta implies that 1 over x to the fourth is greater than b. So as with a lot of these proofs involving epsilons and deltas, or in this case b and delta, we're going to start at the end of it. We're going to start with that 1 over x to the fourth and say, all right, let's see what it takes to get it bigger than b. See if that's even possible. So I set it greater than b. And then I use the reciprocal. We like reciprocals. Reciprocals are happy things because all it does is flip our sign. So we get x to the fourth is less than 1 over b. I can take the fourth root, which gives me x is less than the fourth root of 1 over b. And guess what? X is the same as the absolute value of x minus 0. So this one actually works out really nice. So we have our absolute value, which is less than the fourth root of 1 over b, and that's what we're going to call delta. And so if we say, hey, let delta be this, then we can go that way through it all. We start with that assumption that we're that close, and we end up as big as we could possibly want. So there's our proof. Very rough proof, but it is a proof. All right, I have one more example to show you. So before I throw it up on the board, just remember, limits involving infinity are weird. They're messy. Please, 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 ask questions. If you're taking my class, make sure you come and ask me questions that you need help with. And if you're taking this class from somebody else, bang on their office door until they answer all of your questions. So I do have one more example, and let's take a look at it. So here we go. All right, my last example, and this one's a little bit different. We're going to use an approach that we've learned to compare two functions. So I want to let f of x be x cubed minus 4x squared plus 13x plus 1, and I want to let g of x be x cubed. So if you happen to have taken college algebra from me, we talked about end behavior of polynomials. If you didn't take it from me, hopefully you learned about end behavior of polynomials. Basically, what I said back then is that it's really that first term, the highest power for a polynomial, that decides its end behavior. And so what I want to do here is I want to show that for these two polynomials, that f and g are nearly the same for large values of x. Okay, and so this would kind of show us that the end behavior really is just determined by that first term. So what I'm looking for here is that if they get really, really big, if I divide the two of them, they should end up being 1. Right? If you divide two things that are the same, you get 1. And so we can't, if we do this division, we're not going to get 1. We're going to get a disaster. But if we do the division in the context of taking a limit as x gets very, very big, then we can show that as x gets really, really big, these two functions are going to get very close to each other because, as we'll see, they do have a limit of 1. So we've done this problem before. We're going to divide by the biggest power in the denominator, so we divide by x cubed. If I do that, I get 1 minus 4 over x plus 13 over x squared plus 1 over x cubed, all over 1. And since we know lots of stuff about these, we know that all three of these pieces here are going to go to 0. So they just drop out. We're left with 1 over 1, which is 1. So it's really that first term that determines where a polynomial ends up. And long story short, they get there at about the same, as long as they have the same power, they get there at about the same rate. So isn't that kind of fun? All right, now, interestingly, if I had put, say, a 2 in front of this, this one would have gotten there twice as fast. It would have been twice as big. Or if I had put the 2 on the bottom one would have gotten there twice as fast. So anyway, there you go. Have fun with limits involving infinity, and good luck. Bye.